And I'm going to be talking about how data is actually gets there and getting ready for analysis. So most of the talks here were about data analysis. What I'll be talking about how the data gets from the connected device to the cloud. So who am I? I'm an engineer myself. I've been in business in tech industry for more than 15 years. I'm the CTO of the tech company, of the software tech company called Cesanta. We are Dublin-based, and we are making products connected online. I'm also known as an author of Mongoose web server, which is quite popular in embedded circles. So first of all, I'd like to say a few words about why IoT, and I'm pretty sure that everybody knows what IoT is happening exactly now. So there are different opinions on that topic, but I'm going to tell my own. So, well, in short, I think price and money drives it whole, but let me explain what I mean. So for years, for actually decades, we have an industry called M2M, which means machine to machine. It's quite mature industry, and machine-to-machine communication means exactly that. So like a piece of equipment or electronics talk to other piece of electronics. And traditionally, it's been those projects were quite expensive. So if you take, say, 30, 40 years ago, a computer was a very expensive thing. It costed a lot. The connectivity was also a very expensive thing. So you were talking about dedicated radio or copper lines. And for every such setup, it was an expensive bespoke software development. So only big organizations like government or big enterprises could have afforded to do that. And what we have now, we have actually, unfortunately, don't have a chip with me. So we work with a chip which, in size of a fingernail, and that thick, and they cost in order of $1. So the hardware prices, according to the Moore's law, dropped significantly, and we've got ubiquitous connectivity, which is also cheap. So now it becomes feasible for product vendors to embed those wireless chips into their products, and that would not increase the cost of the product too much. And connecting the product online, it gives a lot of benefits. So a few of the benefits, I'll list it here. So first of all, the product or a device can send back data back to the vendor. And this is the data that could be analyzed after. So suddenly, the link with the customer is not lost. So the product vendor can know and understand how exactly the product has been used. That is something that was not possible before. The second thing is that products could be remotely managed and controlled by vendor or by end customer. So say you can switch off your electricity from your home, like from your phone remotely. So now vendors have an ability, and they want the ability to keep the direct connection with the customer after sale. So all in all, the hardware cost dropped a lot. The connectivity cost dropped a lot. And now it's became feasible for vendors to connect their products. Hence, we have this IoT revolution. It's not new. It has been there for years, the possibility of connecting things. It's just now it becomes really, really cheap. So, and that's why everybody's doing that. So in connecting products online, there are a few specifics that we need to be aware of. Like, first of all, these embedded chips that go into products, which make them connected, they are very, very low constraint. So they're not meant to be used by humans. Therefore, vendors try to keep the prices of these little chips as low as possible. So therefore, those chips are really, really low constrained. And they might not be always on, like our phones or laptops. They could, for example, to save the battery life, some certain sensor maybe deployed somewhere remotely can collect data and then wake up every month or every day and send those accumulated data once a day to the central location. So they might not be always on. The connection could be not TCP, could not be directly to the cloud. It might use some specific radio. So to push the data to the cloud, a certain gateway should be used. Or for example, wearables. Wearables usually use Bluetooth protocol. So to pump the data from the Bluetooth wearable to the internet, we need a gateway, which is usually our phone. So, and also, we want data that is transmitted to be secure, and also we want the chip to be very cheap. And these two things are in conflict because security needs resources. For example, on some chips, just initiating secure connection to the backend, it might take several seconds, sometimes more than 10 seconds, and I have a slide with exact numbers later on. So this is the usual setup of the network topology. We have like connected products on the left-hand side. They are connected to the cloud directly or through some sort of gateway. Then we have cloud, where all the data processing and analytics takes place. And then we have, on the right-hand side, consumers, things or people who access the data. So my talk is mainly about the left-hand side coming to the right-hand, to the middle, so the transfer of the data to the cloud. So, and here I'll give just a quick overview of the protocols that I used to transfer the data from the devices to the cloud. So, first bunch of protocols will be a carrier protocols, and the second batch will be application protocols. So the carrier protocols, first comes Wi-Fi. We all know what Wi-Fi is. It's short distance, roughly 50 meters. It has relatively strong security. It's not low power. It was designed for a really big bandwidth and high throughputs. So therefore, the protocol is not optimized for low power. So you cannot find a Wi-Fi chips with a coin-sized battery. So usually batteries drained pretty fast on Wi-Fi devices. But there is work in progress to make it better in this regard. So second one is Bluetooth. It is low power. The new standard called BLE is it has a pretty high radius. What I have to say is most of these radio protocols use a frequency range on 2.4 gigahertz, which is called ISM range, which doesn't require any licensing. So most of these, as I said, they use 2.4 gigahertz. This next one is Zigbee. Sometimes it's referred as the low power Wi-Fi. It's a bit slower than Wi-Fi and optimized for the transfer of small chunks of data. This one is 6LoWPAN. It's not a radio. It's networking protocol. It's IPv6, and some known and popular protocols are based on top of this. For example, Thread. This is a protocol developed by Nest, which is now Google. They run on top of this, and it uses pretty much like pretty strong security, 100 to 28-bit AES encryption. Next one is cellular. We all know that, like usual SIM cards. And in terms of security, there have been very frequent complaints about that these networks are not really secured well, so the data So the data, the encryption of some of the protocols could be easily broken, and it's not a secret that some governments do actually record all the calls and have an ability to decrypt the data that flows through, and some data is not encrypted at all, like in the first place. So. And that was like a rough overview of most popular carrier protocols. There are dozens more, a big number. Like I didn't mention LTE and some other. I just mentioned a few of the most popular ones. And these are the application level, like HTTP. We all know what is that. It uses a client-server model. It runs on top of TCP. It could be secured with SSL or TLS. It's fairly inefficient. So if we are using a low-power device, it takes a long time to initiate the connection, the request, and get the response, and then the connection tears down. So a lot of resources are used for just one request-reply cycle. And the most secure mode of communication is when the client makes an outbound connection, so the device does not run a server, so it cannot be compromised in principle. The next one is WebSocket. It's pretty interesting protocol. We ourselves use it a lot. It's not strictly speaking an application level protocol. It's a more framing protocol, a carrier protocol that could wrap any data in it. Basically, it provides a very low overhead framing for data, and it's full duplex. So it's not request response. It's a client could initiate a persistent connection with the server, and then any side can send any data back and forth. So it's a fairly popular now, and it's used to do highly interactive applications. So yeah, and it's very often used to tunnel some other protocols on top of it. For example, MQTT protocol, sometimes tunneled through the WebSocket. So and this is MQTT protocol, originally designed by IBM. It has a publish-subscribe architecture. So when there is a central broker and publishers connect to the broker and send the data to the broker in so-called channels. Every subscriber can advertise a channel, can push the data to the channel, and the subscribers can subscribe to the broker and say, I'm interested in that channel or in that channel, and the broker will forward the data to the subscribers. So what's interesting that this MQTT protocol supports a functionality of last will and testament functionality. For example, if the client dies, disconnects for any reason, then the broker will send a notification to all the listeners, to all subscribers, saying this client has died, and this was his last will. So this is a very good functionality in order to keep the subscribers aware of who's alive and who's not. Yeah, and MQTT is very often used to live data transfer, and there are some online services that implement MQTT and have a global coverage. So CoAP is a UDP-based protocol. I would describe it as a HTTP over UDP. So the CoAP messages, they look pretty much like HTTP messages, but over UDP. And the payload is pretty condensed because UDP has a boundary on the message size. And CoAP uses like multiple tricks to shrink the data size. Also, CoAP has something that HTTP doesn't have. It has a resource discovery mechanism. This is called observe. So basically, a co-app client may say, hey, network, tell me who's there. And the co-app, other co-app applications can respond, hey, I'm a application this, I can do this. So it's possible to create an applications that have like discovery capabilities in it based on co-app. And since it uses UDP, the encryption protocol, it needs to use DTLS, which is datagram TLS, transport layer security, which is a variant of TLS, SSL TLS for UDP. And XMPP is another popular protocol, is mostly used for chats, but it has applications for IoT because it's extensible, and there are many extensions written specifically for IoT. So this is a brief overview of the protocols that I used, and again, I didn't mention many other application level protocols. I just chose what I think are most popular right now. The things may change, nobody knows. So some of the challenges that people see when developing IoT setups, like first of all, data privacy and security is the top level concern. There is a big variety of protocols that are available, and each protocol has its pros and cons. Everything depends on the specific situation. So, and latest security standard is TLS, DTLS. TLS 1.2 is the current stable version. And some of the protocols, they allow to use many different carriers. For example, our own Clubby protocol can run on top of pretty much any other protocol on top of plain TCP or MQTT or WebSocket or HTTP and so on. And here comes the challenge. So the modern security, it relies on the generation of true random numbers for the security algorithms. And those little embedded systems, they don't have a good sources for the random numbers, because the random numbers, as usually they are taken from observing real world. For example, on your workstations, mouse movements or keyboard strokes are used as the source of the true randomness. And on small little devices, there are no such things and nowhere to get entropy from. And some systems don't have like disks, and the only kind of way of communicating with the external world, they have network. And some systems use network packet timing to get some random values, but it's also could be faked easily. So the attacker can create packet with specific timing and can fool the embedded system. So the other challenge is that the current public key crypto uses a very expensive mathematical operations to do the encryption. It's called modular exponentiation. It's basically take a value x in the power of e and take modulo of that. And it's really expensive computationally. So here are the values for one of the very low resource chips called IPC chip. And the table here, it shows the key size and the processing time, how much it takes to do this formula. So you can see it can take up to 5 minutes. So basically, for the device, it can take up to 5 minutes to start a secure conversation with other host. So that's a big challenge. So, and thus the conclusions, the hardware chips should implement the random number generator, so the full crypto stack in hardware, not do that in software. They should implement anti-tamper protection, so if somebody opens up the device, it should detect that and stop working. So people should invent security. They should use trusted vendors, and always have disaster recovery plan. So if a breach has happened, to have a plan to recover from it. So this is a conclusions and final notes from my talk. And here we go. We are at stand S120 called Cesanta. Come talk to us if you want your product to be connected. Thank you.
I think we have time for one or two quick questions. Hands up.
Yeah. Some chips that implement a random generator in hardware, they do some take like light sensor data, but it's also weak. It could be forged easily. Basically the idea is to get some sensorial data from environment. That's the idea. But how exactly they do it, it's a specific, right? But you're right, yeah. So taking like data is one of the entropy sources.
All right, and that's actually all the questions we have time for. So Sergey,
All right.
thank you very much.
Thank you.